Well, we started this course by finding the area under a curve and the area in between two curves. And now we're going to look at the area inside a polar graph. So we have a formula for this. The area is equal to 1/2 the integral from alpha to beta f of theta squared d theta. So that's our formula. Okay, we could also write it as 1/2 the integral from alpha to beta of r squared d theta. Okay, we have a provision beta minus alpha must be in between 0 and 2 pi. Okay, and that applies for this shortened form of the formula. Okay, the principle behind finding the area of a polar region is very similar to what we did when we were working with rectangular coordinates and we cut up our area into an infinite number of small rectangles or trapezoids. But in the case of a polar region, we're going to be cutting our area up into segments of a circle. Let's take a look at this. Okay, we're going to find the area of one petal of a rose curve. R equals 3 cosine 3 theta. For the problems in this section, I'm not going to spend a lot of time showing you how to graph them. I did show you how to do polar graphing in the last section, but I will provide you with a picture for each of these problems. I think it's very helpful to have a picture to understand what it is you're trying to find the area of. So using our formula, we've got a is equal to 1/2 the integral, and we want just one of the petals of this rose, which is going to be 1/3 of it. So we're going to go from negative pi over 6 to positive pi over 6. That's going to give us just the one petal that we want. Three cosine 3 theta squared d theta. Okay, and we can factor out the 3. When we have the 3 squared, we can factor out that 9, which gives us 9 over 2 and then we use a power reducing formula, 1 plus cosine theta cosine 6 theta over 2 d theta. Okay, and when we integrate, we get 9 over 4 times theta plus sine of 6 theta over theta, over 6. Evaluated from pi over 6 to negative pi over 6. which gives us 9 over 4 times pi over 6 plus pi over 6. And our final answer is 3 pi over 4. So that's the area of just the one petal. In our next example, we'll be looking at a shape called a limicon, and called that because it looks a little bit like a lima bean. And we'll be looking at the area in between the two loops of the limicon. Okay, here's a picture of the limicon, and here's its equation. R is equal to 1 minus 2 sine theta. And so we're going to look for actually two areas, and we're going to have to subtract one from the other. So area 1 is equal to 1/2 the integral, and we're going to go from pi over 6 to 5 pi over 6 of 1 minus 2 sine theta squared d theta, which is equal, put this down a little, equal to 1/2 this integral (1 minus 4 sine theta plus 4 sine theta squared d theta equal to 1/2 our integral (1 minus 4 sine theta plus 4 times 1 minus cosine of 2 theta over 2 d theta. So this is our power reducing formula, and now we just need to simplify. This gives us 3, oh, forgot my integral. Now I've got 3 minus 4 sine theta minus 2 cosine 2 theta d theta. Okay, finally we're ready to integrate. So it's going to give us 1/2 of 3 theta plus 4 cosine theta minus sine 2 theta. And again, we're evaluating from pi over 6 to 5 pi over 6. And this gives us 1/2 2 pi minus 3 times the square root of 3, which is just pi minus 3 square roots of 3 over 2. Okay, so this is just one part of our integral. We went from pi over 6 to 5 pi over 6. Okay, and this gives us just the area in the small loop of the limicon. Okay, so this is a small part. And we could change this from we go from 5 pi over 6 to 13 pi over 6, and I'm not going to go through all of that again. But this is the area inside the outer loop. So these show me the outer loop. And we'll work through this process again. I see that the second area is 2 pi plus 3 square root of 3 over 2. So to find the area that's in between the two loops, I'm going to have 2 pi plus 3 square root of 3 over 2 minus pi minus 3 square root of 3 over 2. So this is going to give us a total result of pi plus 3 square root of 3. And if I convert that to decimal, it's approximately 8.34. You might recall that when we were working with rectangular coordinate system, that we often had to find the point of intersection between two curves to determine the limits of integration. The same is true for polar graphs, but we have to be especially careful because one point on a polar graph may have more than one set of coordinates that describe it, because we have positive r and negative r. So we need to be very careful. Generally, the way that we're going to find those points of intersection between two equations is by solving the two equations simultaneously. That is, setting one equation equal to the other. Let's take a look at this. If I have r is equal to 1 minus 2 cosine theta, and another equation, just r equals 1, I end up with a circle, and then also a limicon, and it looks like that. And looking at these two shapes, I see that here's a point of intersection, here's a point of intersection, and here's a point of intersection. So if I just took the two equations, and they're both solved for r, so I could just say 1 is equal to 1 minus 2 cosine theta. Well, this obviously means that negative 2 cosine theta has to equal 0, or we could even just say cosine theta equals 0. And when does the cosine equal 0? At pi over 2, and also at 3 pi over 2. Well, looking at my graph, that's this point and this point. So our whole coordinate would be 1 pi over 2 for one point, and 1 3 pi over 2 for the other. But how do I find that point? I mean, it looks pretty obvious that it's the origin, but how do I find that? Okay, I just have to be careful. I really do have to be careful finding the point, because that isn't it. The point's actually out here. Okay, if I'm talking about the circle, I might call that point negative 1, 0. Okay, because if from the center of the circle I go backwards 1 and then I don't rotate it all, that's where I am. Okay, but I could also say, well, if I have a radius of 1 and I go around pi, that's the same point. Okay, so I just have to kind of look out for that when I'm looking at curves. That's just one more reason that you should always make a sketch or graph curves in your calculator before you attack the problem. Now we're going to go back and work another problem that we worked in Chapter 7, and that's finding arc length. In addition, we'll also be finding the surface area when we rotate a shape around an axis. So if we want to find the length of a polar curve, we're going to look at an arc from theta equals 0 to theta equals 2 pi for the equation r equals f of theta equals 2 minus 2 cosine theta. Okay, and this shape is a cardioid. Okay, it's called that because it looks kind of like a heart, like our word cardiac stands for heart. Okay, so the first thing I want to do is find f prime of theta, which is 2 sine theta. So here's my arc length formula. And we'll just use alpha and beta for now for the general formula. And it's the square root of f of theta squared plus f prime of theta squared d theta. Okay, substituting in the values that I'm going to use, we'll go from 0 to 2 pi. We're going to have 2 minus 2 cosine theta squared plus 2 sine theta squared d theta. Okay, we can factor out 2 square root of 2 . just have 1 minus cosine theta under the radical now. Okay, now I'm going to use a trigonometric identity and have 2 sine squared theta over 2 d theta. And this is all still inside the square root. Okay, bringing the square root of 2 out, that gives me 4 here now. And then the square root of sine squared is just sine of theta over 2 d theta, which is equal to 8 times negative cosine theta over 2, evaluated from 0 to 2 pi. Okay, and then cosine of theta over 2 at 2 pi would be just cosine of pi, just negative 1, and I take the negative, that's positive 1. And then also cosine of 0 is 1, so I'm going to have 8 times 1 plus 1, which would be 16. For our last example in this section, we're going to revisit something else we did in Chapter 7, and that's look at the surface area when we revolve a shape around an axis. In this case, we're going to revolve a shape around an axis that's actually touching the shape. So we get something that looks kind of like a donut, but there's actually no hole in the center. Okay, and this is called a pinched torus. Okay, if it's a donut, it's a torus, but we call this a pinched torus. So here's our equation. R is equal to F of theta, which is equal to cosine theta, and we're going to revolve around theta equals pi over 2, which looks an awful lot like the y-axis. Okay, we're going to rotate around the polar axis, this pi over 2. So our equation looks like this. S is equal to 2 pi times the integral from 0 to pi of f of theta cosine theta times the square root of f of theta squared plus f prime of theta squared d theta. Okay, I'm going to replace the f of theta with cosine theta. So I'll have 2 pi from 0 to pi of cosine theta times another cosine theta times this radical. Well, let's replace that 2 while we're at it. Okay, cosine theta, so this is cosine squared theta and then the first derivative would give us sine squared theta d theta. Well, cosine squared theta plus sine squared theta is just 1, so when I take the square root, this is all going to be 1. So now all I have is that s is equal to 2 pi times the integral from 0 to pi of cosine squared theta d theta. Okay, now I'm going to use a trig identity to change that cosine squared theta to 1 plus cosine 2 theta d theta. Oh, that also, we've got to factor out that 2 there. So now I have pi times theta plus sine 2 theta over 2 evaluated from 0 to pi. And this just gives us pi squared for our area. So this is the surface area of our solid of revolution.